Welcome once again to BrilliantMaths.com, where every student has an opportunity to excel in math. BrilliantMaths.com is here to stay and to ensure that you excel. Today's lesson is taken from Brilliant Maths Module 7, so grab a copy and let's go to class. In this lesson, we want to look at symmetry. What do we mean by symmetry? Mathematically, symmetry exists when one shape becomes exactly like another, when flipped, slid, or turned. Not all objects have symmetry. If an object is not symmetrical, it is called an asymmetric object. Let us look at line symmetry. Line symmetry exists if a shape can be divided into two identical parts, which are mirror images of one another. So the line dividing it is called an axis of symmetry. So the line dividing that shape into two identical parts is called an axis of symmetry. Look at the lake on your screen. The reflection in this lake has a line of symmetry. You can see the line reflecting what's on top in the lake. So that's a line of symmetry. Point symmetry. Point symmetry is when every part has a matching part, the same distance from the central point, but in opposite direction. We'll look at that shortly. Then we have reflective symmetry. A shape has reflective symmetry if it has one or more lines or planes of symmetry. So when a shape has more than one line of symmetry, it is said to have reflective symmetry. Then we have rotational symmetry. A shape has rotational symmetry when it still looks the same like the original shape after a rotation. So when you're talking about rotational symmetry, then you can talk about the order of rotational symmetry. How many times will the shape look exactly like the original shape, turning it through 360, through a complete revolution? The number of times that that shape will look exactly like the original is the order of rotational symmetry. Let's look at an example here. In the example, it says, which of these shapes have point symmetry? The first shape is labeled A. The shape A does not have a point of symmetry because there's no matching point on the opposite side. But look at shape B. The shape B has a point of symmetry. A line drawn from a point on the figure through the center that will have a matching point on the other side, on the opposite side. So you can see that that shape, which is in form of S, has a point of symmetry. Let's look at the next example. We have the word math, the letters of the word math. We have M, A, T, H, all in uppercase letters. We can see the dotted lines showing the lines of symmetry. So the letter M has one line of symmetry passing through the midpoint of the alphabet. The letter A has one line of symmetry which divides the alphabet into two equal parts. The same with the letter T. It has one line of symmetry through the middle. And then the letter H has two lines of symmetry, as we can see. one horizontal one, and a vertical one. Let's look at the next example. It says, write down the number of lines of symmetry of these shapes. We have two shapes there. The first shape is made up of two circles and several lines. If you look at the lines properly, you'll find out that each of the lines pass through the center of the circle. And each of those drawn lines is a line of symmetry. Look at the solution. When you extend each of those lines, you'll find out that it splits the circles into two equal parts. Then in the next one, it has 8 lines. And all 8 lines divide the circle into two equal parts. So that circle, the second shape, has 8 lines of symmetry, while shape A has 4 lines of symmetry. I hope this makes it clearer. In this part of the lesson, we want to learn how to find the order of rotational symmetry for any shape. So we have this rectangle A, B, C, D. How many times will the rectangle look exactly the same as you turn it around within 360? How many times will it look like the original shape? That will be the order of rotational symmetry. So we have rectangle A, B, C, D. If you turn it 90 degrees, then it stands upright like this. Turn 90 degrees. So it becomes A, B, C, D. Does this look exactly like that? No, not yet. Then turn another 90. That is, after 180 degrees turn, it looks exactly like the original shape. So that's the first time it looks like it. Then turn again another 90 degrees. It looks like this. So it becomes B, C, D, A. So after 270, it's not exact. Then you turn again another 90 degrees, making 360. Then it looks exactly like the original shape. So how many times did it look exactly like the original shape? It is twice. 1, 2. So a rectangle has rotational symmetry of order 2. As you turn it around 360, it looks twice exactly like the original shape. The first time is after 180 degrees turn, and then the second time is after 360. So let's look at a square then. For a rectangle, we know that we have the length and the width are different, but a square has equal sides. So that means that for a square, for every 90 degrees turn, it will look exactly the same because the length and the breadth are equal. So a square would have rotational symmetry of order 4. As you turn it the first time, 90 degrees, it will look like the same shape. Another 90 degrees, the same. Another 90, the same. And then the fourth one, the same. So a rectangle has rotational symmetry of order 2, while a square has rotational symmetry of order 4. We want to look at point symmetry. Look at the parallelogram on your screen. A parallelogram has no axis of symmetry. However, if you draw the diagonals AC and BD to intersect at O, like in figure 8, this point is called the point of symmetry. This is because any line passing through O, there are 2 points, one on each side of O, which is equidistant from O. The parallelogram is said to have point symmetry. When a plane figure has point symmetry, it appears not to have moved after rotation through 180 degrees. Therefore, the parallelogram has rotational symmetry of order 2. Let's look at this example. The letter S. As you can see on your screen, if you rotate the S through 360 degrees, about the marked point, it will have two identical positions. One after 180 degrees and the second after 360. So X has rotational symmetry of order 2. Let's look at the next set of shapes. For these shapes, state the order of rotational symmetry. The first one is a triangle. The second one, and then the third one. The first shape can only look exactly the same after 360. At 360, that's the only time that triangle will look like the original shape. So it has rotational symmetry of order 1. The second shape has rotational symmetry of order 2. As you can see, if you turn it after 180, it will look exactly like the original shape. So at 180 degrees and at 360 degrees. Same with the third shape. It has rotational symmetry of order 2. Because if you turn it after 90 degrees, it will look different. But after 180, it will look exactly like the original shape. At 180 and at 360. So it has rotational symmetry of order 2. Let's look at another example. We saw these shapes earlier on in the first lesson. The first shape is a circle with another smaller circle inside and lines. For the first shape, when it is rotated 45 degrees, this is the result. It's on your screen. You can see how it looks. It is not quite like the original shape. But after 90 degrees, it will look like the original shape. So it will look like the original shape at 90 degrees, at 180 degrees, at 270, and at 360. It gives you the same shape. So it has rotational symmetry of order 4. And then the second shape, that shape has rotational symmetry of order 8. Every 45 degrees, it looks exactly like the original shape. We are still looking at the symmetry of special 2D shapes. So we have a kite. The kite is kite ABCD. The line AC is a perpendicular bisector of the angle at A and C. It splits the shape into two equal parts, meaning that triangle ABC and triangle ADC are congruent. The sides are equal, the angles are equal. So AC is a line of symmetry or axis of symmetry. And that's the only line of symmetry that this shape has. So the kite has one axis of symmetry or one line of symmetry. Then here we have a square. So this is a kite. Then the second shape is a square. For the square, all the sides are equal, as we can see. And then the diagonals of a square are also equal. So this first line is a line of symmetry. If you fold the square on that line, it folds into two identical parts. The diagonal is also a line of symmetry. If you fold a square along the diagonals, it will fold into two equal parts. Then the line in the middle is also a line of symmetry, and then the other diagonal. So a square has four lines of symmetry. So we can see the four lines of symmetry. Then we have a parallelogram. The parallelogram has no line of symmetry. It has no axis of symmetry. If you draw the diagonals, it will not be a line of symmetry. There's no way you split the shape to get a line of symmetry. However, it has point symmetry, like we had seen earlier on. So still looking at symmetry of special 2D shapes, you can see the triangle on your screen. It's an isosceles triangle. The isosceles triangle has two equal sides, so the base angles are equal. So it has one line of symmetry. You can see the line dividing the triangle into two equal parts. That's for an isosceles triangle. Then look at the equilateral triangle on your screen. For an equilateral triangle, all the sides are equal and all the angles are equal to 60 degrees. So the equilateral triangle has three lines of symmetry. It has three axes of symmetry. Every line from every vertex to the other end divides the shape into two equal parts. So an equilateral triangle has three axes of symmetry. A scalene triangle has all three sides of different length, so it does not have a line of symmetry. All sides are of different length and all the angles are also of different length. So there is no line of symmetry for a scalene triangle. Look at your screen. You can see the table summarizing the symmetry of quadrilaterals. A square, we're looking at the figure or the shape, the number of axes of symmetry, the order of rotational symmetry, and whether or not it has point symmetry. So for a square, it has four axes of symmetry, like we said earlier on. It has order of rotational symmetry is 4, and it has point symmetry. A rectangle has two axes of symmetry, and the order of rotational symmetry of a rectangle is equal to 2. And a rectangle also has point symmetry. A parallelogram has no axis of symmetry, like we have learned, but the order of rotational symmetry for a parallelogram is 2. A parallelogram also has point symmetry. Then look at a rhombus. Think about a rhombus. A rhombus has two axes of symmetry. Order of rotational symmetry is 2, and it also has point symmetry. A kite, like we saw earlier on, has one axis of symmetry, and the order of rotational symmetry is 1. But it has no point symmetry. An isosceles trapezium has one axis of symmetry and rotational symmetry of order 1, but no point symmetry. And a scalene trapezium has no axis of symmetry, rotational symmetry of order 0, and also a scalene trapezium has no point symmetry. So this table summarizes the symmetry of various quadrilaterals. And finally, let's look at that example. We have those three shapes, the triangle, the circular shape with semicircles in between, and the double arrow. As you can see, the lines of symmetry are indicated. The triangle is just like an isosceles triangle with one line of symmetry. The spherical shape has two lines of symmetry, as we can see. Look at the semicircles in the middle. So it has two lines of symmetry, and the double arrow has two lines of symmetry. I hope this makes it easy for you to identify lines of symmetry, order of rotational symmetry, and whether a shape has point symmetry or not. In this part of the lesson, we want to look at how to recognize symmetry of three-dimensional shapes, to recognize the lines of symmetry, the order of rotational symmetry, and the properties. Take a look at your screen. If a solid figure such as the sphere on your screen is cut into two equal parts, as shown, the plane of the cut is called a plane of symmetry. So look at the screen, look at the sphere. See the plane of symmetry where the sphere is cut. So a plane of symmetry divides a 3D solid or a three-dimensional solid shape into two congruent solid shapes. So it divides it into two such that the two parts are equal. So if you look at that sphere and you see where it is cut, you'll see that it's been cut into two hemispheres. Exactly, it's been cut into two hemispheres. Look at the cuboid. The cuboid has also been cut into two equal parts by the plane ABCD. Hence, the plane ABCD is a plane of symmetry for the cuboid. Can you see the plane? It has cut the cuboid into two equal parts. Note that solid figures cannot be reflected in a line. They must be reflected in a plane mirror. Hence, the term plane symmetry. Take a look at the prism now. Can you see the plane symmetry? Where it is cut. A prism whose cross-section is a regular n-sided polygon has n+1 planes of symmetry. So if the prism has n sides, then the number of planes of symmetry will be n+1. So for example, a pentagonal prism. A pentagon has 5 sides. So a pentagonal prism will have 6 planes of symmetry. One plane like this. And then 5 planes like you can see on your screen. Then let's look at reflective symmetry. A shape has reflective symmetry if it has one or more lines or planes of symmetry. If it has one or more lines or planes of symmetry, then it has reflective symmetry. A three-dimensional shape or a three-dimensional object has rotational symmetry if when rotated about a central axis, it looks the same at certain intervals. When you rotate it about a central axis, it looks the same at certain intervals. The number of times it looks the same at certain intervals during a complete revolution is called the order of rotational symmetry. We have seen that before. The cylinder and the cone both have an axis of symmetry. So look at the screen. You can see the cylinder and you can see the axis of symmetry, the line of symmetry, and also for the cone. The next, a prism whose cross section is a regular n-sided polygon has order of rotational symmetry of order n. For example, a pentagonal prism has rotational symmetry of order 5. It must be a regular shape for that to happen so that all the sides are equal. The cuboid, like we said earlier on, has rotational symmetry of order 2 about the axis shown. I think these examples are enough for now. In this part of the lesson, we want to look at symmetry of circles. Let's look at some facts regarding the symmetry of circles. So we have a circle, and the first fact we're looking at says that if two chords are the same length, then they are the same distance from the center. So we have a chord AB from one part of the circumference to another, but as we can see, it's not passing through the center. So we have a chord AB and chord CD. So what this fact is saying is if AB is equal in length to CD, so the two chords are equal, then it only means that both chords are the same distance from the center of the circle. It only follows because the only part where the chords can be of equal length is when they are of equal distance from the center of the circle. So that implies that OM is equal to ON if AB is equal to CD. Then the second fact states that the perpendicular bisector of a chord passes through the center of the circle. So we have a chord AB. Remember, a chord passes through one side of the circumference to another without passing through the center. So this is the chord. The only chord that passes through the center is the diameter, because the diameter divides the circle into two equal parts, from one part of the circumference through the center to another part of the circumference. So this is called AB. And then the fact says that this broken line, if this broken line divides AB into two equal parts, then it passes through the center. That means that this line, this perpendicular bisector, is passing through the center of the circle. That is one fact that we need to know. And then finally, from the third diagram, we have the circle with center O, and then we have two radii, OA and OB. So if there are two radii, then that means they are both equal. So the fact says that the two tangents from the point C, so you have the tangent BC and the tangent AC. What this fact means is that the two tangents from the point C to the circle are equal in length. And that is obvious because OB is a radius and OA is a radius, so they are both equal. And then OC is common to both triangles, so it only implies that AC is equal to BC. So the two tangents from the point C to the circle are equal in length. You'll find this very useful when we start doing circle theorems, and that is going to be our next lesson. I hope you enjoyed that lesson on symmetry. We had rotational symmetry, we looked at point symmetry, lines of symmetry, reflective symmetry, and even symmetry in circles. Subscribe to brilliantmaths.com so you can get lots and lots of practice. My name is Ngozi Orevogene, and always remember that maths is fun and you can excel in it.